Welcome back to the course in Nuclear Medicine Physics. Today we're looking at a way to evaluate image quality in a task-based way.
Gifted with a truly brilliant mind. I met Abhinav when we were both at Johns Hopkins University. He ended up moving to departments of biomedical engineering and the Mallinckrodt Institute of Radiology at the Washington University in St. Louis, where he's an assistant professor. And he's the PI of the Computational Medical Imaging Lab. And again, as I mentioned, he was previously faculty at the Department of Radiology at Johns Hopkins University. Abhinav obtained his PhD from the College of Optical Sciences, University of Arizona, where there's very influential thinking and school of thought on task-based image assessment going on, and he's going to talk about some aspects of that today and some of the leading perspectives on this area that he's been leading on himself. And he also obtained his master's from University of Arizona in electrical and computer engineering. He has had multiple awards. He's been awarded with a number of awards and a number of very interesting funds, including the Trailblazer R21 Award for developing reconstruction and image analysis methods for SPECT. He's done work in SPECT imaging and PET imaging, but not just that. He's had very fascinating works on optical imaging, diffuse optical imaging, and also on diffusion MRI. Overall, over the years, it's just been a real pleasure working with Abhinav. I've learned from him. We've defined joint projects together, and we continue to collaborate and to work together and to interact. So, without further ado, thank you for accepting our invitation, Abhinav, and thank you for being here.
Well, thank you so much for the kind introduction, Arman. And needless to say, I consider you as a close friend, someone whom I often go to when I need advice, but also have enjoyed multiple fascinating discussions with you, both on research, on the topic of task-based image quality assessment, actually, and philosophically too. So very excited about giving this talk. Very excited to be here, and I understand that this is a class on nuclear physics. So my talk will be about task-based image quality assessment in medical imaging, but there will be a special focus on nuclear medicine. This is actually also a part of my own research. My own research on task-based image quality focuses heavily on PET and SPECT. So I'll be talking specifically on trying to give examples from those imaging modalities. So before we get started, I should share that actually I teach in the fall semester. So in the spring semester, I'm actually not teaching. So this is good. It's nostalgic in some sense because this is the first lecture I'm taking this semester effectively. So it's great. For the administrative portions, here's my email. Feel free to reach out to me if you have any questions that you would like after this presentation or after this lecture rather. But feel free to ask me questions right in the middle. I really enjoy discussions. I think discussions are very helpful to stimulate nice thoughts, but in addition to that, also provide an opportunity for a much more group-based, community-based learning. So if you have a question, someone else is going to have that question. So it's great if you can ask that question and I can respond to that, and that can help everyone understand the material better. Now, I provide here some additional reference material. The topic that I'm talking about has had a rich and vast history, and I think one lecture is definitely not enough to, maybe even an entire course is not enough to do justice to the amount of research that has happened in this area. I'll try to do my best, but here are some references that I provide, which you could go to after this lecture to read more about this. One reference I would highly recommend is the first one, the book Foundations of Image Science by Harrison Barrett and Kyle Myers, chapter 14 of the book. Then I quote a second reference, which is actually a proceedings paper, and I cite this proceedings paper because towards the end of, in the second half of our lecture, rather, we will talk about some specific examples of applying task-based image quality assessment, and this reference actually covers that example. Then Harrison Barrett, as in Harry, his papers on objective assessment of image quality. There's a series, 6 papers actually published, 5 of which published in JOSA A, 1 published in Physics and Medicine and Biology. Outstanding reviews, outstanding material, which I would heavily recommend if you're more interested in this field. And a recent paper on virtual clinical trials in medical imaging that would be providing a practical paradigm to perform this kind of task-based image quality assessment. This is, again, by no means exhaustive. There are multiple other references. My apologies to some of the references that I've missed due to the space constraints, really. But this is a really vast and huge field. Let's get into it then. So the objectives of this lecture are going to be to introduce the topic of image quality evaluation. We are going to motivate the need for task-based assessment of image quality evaluation. We will then introduce the key components of task-based image quality assessment. I specifically use the word introduce here because I will not be going into details of each of these components. Like I said, I think each of these components could themselves be multiple lectures by themselves. I'll try to provide some references. So in case you're interested, you can go in there. I know that I'll probably stimulate your interest a little bit, and then I'll leave you unsatiated. So please go ahead and look at the references if you get excited about these topics. Of course, I'm happy to talk more about this later with you. We can please feel free to send me an email. We can set up an appointment as well to talk about these things. My goal here is that instead of going into details, I want to provide some practical examples of task-based image quality assessment that will give you much more of a feel for how this thing is done. Because right now, and I can understand, you may feel like it's a really abstract concept. How do you even do this thing? So that would the practical examples would provide you with some concrete, things to hang on to understand how to perform this task-based image quality assessment. So firstly, what's the need for image quality evaluation? So since this is a class on nuclear medicine imaging, I chose an example on SPECT. So in SPECT, as you may have learned in this class, we have an object, a radio tracer distribution that we are imaging. We have a system that consists of a collimator and a detector surface. And then we have an image that's formed after that from the projections that are obtained. Now, this choice of collimator is very important. We could have a collimator that has very fine bores, so it has low sensitivity, and it allows only photons that come in perpendicular to the detector surface or approximately perpendicular to the detector surface. So it has high resolution, but as a result of that, it also blocks a lot of photons, and so the sensitivity or the photon sensitivity of the system is pretty low. Now, in this case, because you have a high resolution collimator, you would obtain an image that has high resolution, a good resolution, but it may have poor signal to noise ratio. So the images may look noisy. In contrast, you may have a collimator that has coarse bores. So it allows a large number of photons, but from different directions. So now you have a collimator that has higher photon sensitivity, allows a larger number of photons, but a lower resolution. So now what you would obtain is a reconstructed image that has poor resolution. You can see it's kind of blurred here, but it has good signal to noise ratio. So now the question that gets asked is, which collimator should I choose? Any thoughts on this? Anyone? Which one is better?
Yeah, feel free to comment either by turning your screen on, saying something. You could also type in the chat if you wish.
So I see that there are 3 chats.
Yep.
Okay, so some
comments are coming in. Yeah.
So Ali has kind of stolen my thunder here by saying it depends on the task. But then, yeah, there are some very other interesting answers as well. It depends on the application. It's a trade-off, but the first one seems to be easier to compensate. None of them, or let's say both of them together. And I think all of these answers are trying to go towards the same thing, right? I mean, it's even more new message, right? So something in between. So all of these answers are kind of trying to go to the same thing. Like, why did we acquire this image in the first place, right? Well, it depends on the goal, as Judy mentions here, right? Why did we acquire this image in the first place? It was for some reason, right? I mean, we wanted to either detect the tumor, or we wanted to measure uptake within the tumor, or we wanted to measure the volume of the tumor, or maybe it's measure some heterogeneity which is not present in this tumor, but we wanted to measure some heterogeneity within the tumor, right? So the question of why did we acquire this image in the first place? It was not because we wanted to get a beautiful looking image, right? Because an image may look beautiful, but what does it matter if it does not help a radiologist perform the task that's required from the image or not? Uh, so and we argue, or we hold the view that when we do image quality evaluation, it should focus on the task that's required from the image. Now, there are approaches for image quality evaluation, and there has been a lot of research in this direction. One of the metrics that's used is contrast to noise ratio, and I'm sure many of you must be familiar with this metric. And this metric has definitely has applications, but here is an example where we see the limitations of this metric on performance in tasks. So now imagine that this is the signal that you're trying to detect, okay? And you have this noisy background that you're trying to detect this signal. And so you have this background, and here is your signal that you're trying to detect. All these images that I'm showing you in each row have equal contrast to noise ratio. But I think I don't even need to ask. Anyone will say me that the images on the right have easier ability to be able to, for the signal to be detected compared to those on the left. Unless anyone has any wants to dispute me on that, let me move to the other figure of merit, visual appearance. Sure, visual appearance is often a metric that's used, but it's difficult to quantify this. And we would like to quantify because we want to be able to design our system based on rigorous quantifiable engineering principles. One more figure of merit that comes up often is mean square error. So this figure of merit looks at some measure of difference, rather a distance between the object that we are trying to image and the image that's formed itself. But then this is a bit like comparing apples and oranges, because images are discrete. Images are pixels or voxels in 3D, whereas we humans, we are not pixels, we are continuous. So comparison using mean square error, where we are trying to find some difference between this continuous object to this discrete image, may not be accurate. Now, to further illustrate my point, here I show you 5 reconstructions. So here is the original sort of object that we are imaging. And I'm showing you 5 reconstructions that have the same mean square error compared to this original object. So if someone were to ask the question, well, which of these reconstructions is the best? Well, they have the same mean square error, but one of you may say, well, looks like B and F are better, because if the goal was quantifying this signal in this image, then I would have liked B and F compared to like E or C. For those of you who come from an electrical engineering background, Lena must be a famous person to know. And here is Lena on A, and here are 5 images that have been obtained. Again, all of which have the same mean square error compared to this original Lena. Which of these is the best? So this helps to show, I'm trying to show the point here that, which one, yeah, B seems like, if it's a Lena image, then B seems like the best, because again, so, and that's a good point, right? Why does B seem like the best? Because with Lena, our goal is to try to see if, how perceptually, how good does the image look like? And here in this case, it does seem like the image B looks like. But again, it's going back to the task, right? Why did we acquire the image in the first place? Here in the case of Lena, it was to actually get a good image, an image that was visually pleasing. Whereas in medical images, it may not be visually pleasing. It may be, the task may be detection of a tumor. It may be quantification of some parameter. So that all that motivates again the task-based evaluation of image quality. So in scientific and medical imaging, images are required for certain tasks. So image quality should be assessed based on how well the imaging system or algorithm performs on this task. This calls for a task-based objective assessment of image quality. Now, to make this make this case even more concrete, let me present you a very contemporary example. So we are living in a brave new world of artificial intelligence. So let me show you why this task-based evaluation becomes even more important in this brave new world. So now there's significant interest in using artificial intelligence methods for low-dose SPECT imaging, low-dose PET imaging, low-dose CT, and so on. I'm sure going to show you an example from low-dose SPECT. Now, conventionally, methods for that are based on artificial intelligence are evaluated using fidelity-based metrics, such as root mean square error, something we just discussed, peak signal to noise ratio. Another metric is structural similarity index. So we conducted a study in the context of myocardial perfusion SPECT to assess whether these metrics of root mean square error or structural similarity index yielded similar interpretation as performance on the clinical task. So I'll not go into the details of studies. Let me just say that we had some kind of ground truth tracer distribution. We used some imaging models to obtain normal dose projections and low dose projections, which were reconstructed using certain pure physics-based approaches. If you're familiar, OSEM, ordered subset expectation maximization approach, was used to obtain the normal dose image and the low dose image. Now, this low dose image was then denoised using a CNN-based denoiser to give us a low dose CNN denoised image. This study was done in 3D with 10,000 3D images used for training and cross-validation. The methods were then evaluated 2,000 test images, and the study was conducted at multiple lower dose levels, including 20%, 10%, 5%, and so on. So let us look at the qualitative evaluation, the evaluation based on visual analysis. Now, clearly, if you look at these images, and I'm showing you two examples here, it does seem like the low-dose CNN denoised images were indeed looking less noisy, smoother, compared to the low-dose physics-based approach, the low-dose OSEM-based approach. You can see it looks more noisy here, whereas this is so much more smoothed out. Looks so much more closer to the normal dose image, the CNN denoised image. So visually, the AI-based method seems to yield less noisy and higher quality images. Now, then we looked at this conventional figures of merit, something we talked about earlier, root mean square error. And what we found was that the root mean square error obtained using the AI-based approaches was actually lower than the one obtained using pure physics-based approaches. And lower here is better, lower error, right? So this says that the AI-based approach is better. We looked at peak signal to noise ratio. The AI-based approach had a higher peak signal to noise ratio, again saying that's better. And when we looked at structural similarity index, again, the AI-based approach had a higher structural similarity index, again indicating that's better. It's more similar to our normal dose image. So evaluation with these conventional metrics concluded that the AI-based method is yielding improved performance at all the lower dose levels. Now, all that's good. Then we looked at the task. So what is the task from these images? The task is actually detection of the myocardial perfusion defect. So this was a study, again, I should emphasize, it was in the context of cardiac SPECT. And so the objective is to be able to detect these cardiac defects in the image, which the radiologist then uses to make recommendations about whether, or as one of the decision points to make a recommendation on whether the patient should undergo further surgery or not. So what we did here was that we have these low dose CNN denoised images, and we have our normal and low dose images obtained using the pure physics-based approach. And we did an observer study, an observer here meaning some kind of decision strategy that uses the images to make a decision on whether the defect is present or absent. And what was the study on? It was on the defect detection task. Now, for this purpose, there is this model observer that has already been developed that we used. This was done over 2,000 patients. I should mention that this was all in simulations. That's why we know the ground truth, so that we could do the study. And here are the results of the observer study. Rather alarming, actually. If you look at the AI-based ROC plot, and I'll go into more details on this, what we observe is that the AI-based ROC was actually lower than the pure physics-based ROC. And I'll go into what an ROC means later in the lecture, but essentially this was saying that on the task of quantifying or detecting defects, the AI-based approach is actually performing poorer compared to when using just the pure physics-based approach. This was not just true at 20% dose. This was true at 10% dose. This was true at 5% dose. So for all the dose levels, the AI-based approach had a lower ROC curve compared to that obtained with the pure physics-based approach, indicating that the AI-based performance on the task of detect defection is actually poorer compared to that obtained with the pure physics-based approach. We also looked at the AUC values, and here the AUC values are something that again quantify like defect detection accuracy, and the AUC values obtained using the AI-based approach were lower than the obtained with pure physics-based approach at all the lower dose levels. So I apologize that I've introduced these terms called ROC and AUC before actually defining them, but the key message I want to convey here is that on the task of detecting perfusion defects from low dose images, the AI-based approach actually yielded poorer performance than the simple physics-based approach.
If I may comment, Abhinav, yeah, I remember when your group presented this work at the Society of Nuclear Medicine and Medical Imaging, SNMMI, and it was one of the very early evidences and leading works in our field to really make people, cautious about over-optimism about AI methods. Because people were starting to see that CNNs sometimes do over-smooth images, but they sort of said, well, some of these metrics seem to indicate it's really good, but then you showed evidence that it doesn't necessarily improve performance and it can even degrade performance, which is what you're saying.
Yeah. Well, thank you, Arman. Thank you for that feedback. So actually this, I should just take a slight digression and say that we were actually very excited about applying the AI-based methods ourselves. And again, the point here is not to say that the AI-based methods do not work. They do work. I'll show you examples of where they do work. But the point here is that there is a need for task-based evaluation. So here is the further illustration of that. So here was a case where on the top row the defect was absent, and the AI-based low dose kind of created the defect. You can see the slight blip here. I'm not a radiologist myself, so I'm not going to, but my radiologist collaborators tell me that there's a defect that's present here. And here's a defect present case. You can see the slight blip here, slight lower activity here, and the AI-based method kind of washes out that effect. So even though the AI processed images visually look less noisy, they may not do well on the clinical task. So the takeaway point, evaluation of imaging methods using conventional figures of merit yielded different interpretation as objective evaluation on specific clinical tasks. So this calls for a need to evaluate imaging methods using task-based image quality evaluation studies. But how? So before I go to the but how, there are two comments I see on chat. So thank you for the feedback, Ali. Arash has a comment. In this work, the ROC of AI performance is worse enough that it make it not reliable. Yes. Well, I think it depends on how we define reliability here. The point of this study was to basically demonstrate that the evaluation using conventional metrics may not provide us with the right interpretations. But the AI-based method did perform. From this analysis, we know how well the AI-based method performed. And so we can then use this analysis to, when in future we apply this AI-based approach to know how well it will perform in these tasks. So hopefully that answers your question. I think the eventual question of reliability would actually be answered by a physician who would then make an assessment of is this actually reliable or not. So I don't know if there's another message that came up, but before we move on to the but how, because this is really abstract, and I'm talking about all this task-based image quality evaluation. It's really nice, seems like a nice concept. In my first word, like, yeah, this is what we should do, but I did not know how we should do it. What are the tools that are available for me to do task-based image quality evaluation? Are there engineering principles? Are there mathematical principles that are defined for this purpose? So that's the next part of this lecture. Before that, are there any questions? let me move on to the how. So let us say that we have a set of original objects, some kind of patient population, and we have two different systems, system A and system B, which are giving us these images. Now, which system is better? So for answering that question, we first ask another question. We define a task, specify the task. Why are we acquiring this image in the first place? Is there a detection task that we are doing here? Is there an estimation task that we are doing here? Is there a combined task maybe? Once we define the task, then we obtain an observer to extract the task-specific information from the image. So this leads to the task-specific information being extracted. Now, this task-specific information could be the tumor volume. If that's the parameter I'm interested in estimating, then I define an observer, some kind of mathematical or human-based algorithm that is able to identify to get that task specific information for me, such as here's a tumor volume or here's an uptake within the tumor. Now, once we do this, we determine which system gives better task performance. So for this purpose, we define figures of merit that use the task specific information to quantify task performance. So again, this example of tumor volume, well, a figure of merit would be how accurately did we measure the tumor volume, or how much was our, how precise were we in measuring the tumor volume. And these two figures of merit have their own needs and own importances, again, depending on the eventual goal that we are striving towards. And then once we have determined which system gives better task performance, we have therefore objectively evaluated the systems. So let me give you some examples here. One is detection task. Task is detect if defect is present. The observer could be a radiologist or some kind of mathematical algorithm. A potential figure of merit is detection accuracy. How accurately could I detect if the defect was present or not? A defect could be like a tumor, or it could be like a cardiac defect that I showed you on the previous slide. Another task could be estimation. Already talked about estimation of tumor volume. Observer is some kind of estimation technique, right? Something that estimates what the tumor volume is. A potential figure of merit is accuracy of the estimated volume. So that brings us to the components of the objective assessment of image quality, or OIQ study. Because objective assessment of image quality is just a long phrase, so I'll just use OIQ to refer to it. So it consists, as we have seen in the previous kind of flow chart, consists of 4 parts. One, specification of the task. Define the task that you are acquiring these images for. Then description of the object model and the imaging process. You need this so that you can then describe the data that you have obtained, the images which you have obtained. Then the process to extract task-specific information, as I showed you in the previous slide. And finally, the figure of merit to quantify task performance, as again I showed you in the previous slide. So let's go into each of these components one by one. Again, I'll very briefly introduce them. As I have said, each of these are worth a lecture or a couple of lectures themselves, but I'll try to provide you with some initial starting points, really. So task could be one of detection. So the task is detect if defect is present. I've already shown this example, but there could be other detection tasks. Is a tumor benign or malignant? What's the stage of the tumor? This is also, even though it's not exactly a 1 or 0 binary detection task, this is more like a classification task, but this is also can be considered as a broad detection task. So what's the stage of the tumor? And more general classification tasks all fall into the detection task category. Arman, I would say, actually, I'm not able to see the chat. So if anyone has a question on chat, if you could please
Absolutely.
let me know, I would appreciate that. Then the next is estimation or quantification task. So here the task could be estimate tracer uptake within certain regions of the brain. So this is a SPECT image, and we are trying to estimate tracer uptake within, say, caudate, putamen. I'm also very interested in the globus pallidus region, so I've shown that here. Other quantification tasks: metabolic tumor volume in oncological FDG PET image, tumor location in a SPECT image, radiomic features from PET images, this huge emerging field of radiomics where we are looking at things such as intratumor heterogeneity, tumor shapes, and so can we, and these are broadly referred to as radiomic features. So quantification of these features from PET images. But then there could be joint detection / estimation tasks. Example, detect if tumor is present, and if present, quantify uptake within the tumor or quantify the volume of the tumor. Then we go on to the second component of the OIC study, describing the object model and the imaging process. So firstly, describing the image object model requires us to very deeply think about what is the thing that we are imaging, what object property are we imaging. For example, we say we image a patient, but in nuclear medicine, we are not imaging the patient. What we are imaging is the radio tracer distribution, the activity concentration within the patient. In X-ray, we are measuring the attenuation distribution of the patient within the patient. In diffusion MRI, we are measuring the diffusion coefficient of the region. So here's a trivia question. Can anyone recognize this X-ray image? Actually, it's kind of mentioned there, but you see this ring here? So actually, I have mentioned this. This is by William Wrongton, actually. So this is one of the first X-ray images that he took. It's his wife. he put her hand, wrist in the X-ray system that he had designed, and then he got the image of that. And that's one of the first X-ray images that was obtained. So I think these days this would require an IRB approval to be done, but those days we did not have that much of IRB approvals. So next is describing the object model. Now, this is a very important part of task-based image quality evaluation. We need to be very realistic in describing the objects that we are imaging. If we are going to image spherical tumors, if we are going to image and make inferences about patients, our objects better look like patients. Because if they don't, then we will be making inaccurate inferences about them. This is specifically important in the context of deep learning. So for example, you could have a deep learning algorithm that is designed to detect spherical tumors very well. And every time it gets spherical tumor, it says, oh, there's a tumor, right? But in reality, no tumors are spherical. So this algorithm would just spectacularly fail when it is actually applied to an actual patient. So it should account for the physical and statistical properties of the object to be imaged. So we should image patients, and we should also account for patient population variability. This is a very important aspect again. Now, ideally, this should be done with patient populations, but this is logistically challenging. There are multiple challenges, time-consuming, expensive, requires a lot of paperwork, IRB approvals fairly. I mean, it's important that when patients are imaged, then these kind of approvals be obtained. But that means that imaging technology development can take up a lot of time. So one alternative to this is to use simulations. Simulations provide us with an opportunity to evaluate imaging technology with known ground truth, with the ability to model the patient population variability, the physiological uptake, changes in anatomical parameters, and so on. And so there are some simulation-based tools that are available for this purpose, and there's a lot of research in this area on making these simulations even more realistic. One of the most widely used tools is this extended cardiac and torso phantom, or the XCAT phantom. Then another one is a nerve-based brain phantom. This was actually pioneered by Dr. Arman Rahimi himself. Then we have also been developing some approaches that actually try to incorporate realism. We try to use patient images as background. The idea here being that oftentimes we are not very interested. We want the patient background to be as realistic as possible, but we are not interested in the ground truth there. What we are interested in is the ground truth of the thing that we are trying to say, estimate or detect. For example, a tumor. So we use patient images as background, and then we have developed lesion insertion methods that very realistically are able to insert these tumors in these patient images. And we have actually recently shown that this approach is able to give, again, I'll probably try to avoid use of technical lingo here, but as evaluated using human observers, they were not able to distinguish our phantoms from phantom generated images from the real clinical images. So details are present in this proceedings paper here. So then comes the second part, which is describing the imaging process, and for which we have an imaging equation. So let's say here is an object that we are imaging, F. Here is some imaging hardware. I've used a very simple hardware such the lens system. And here is the image that we get. But there's a problem, right? I mean, no images are like this. They are actually have a lot of noise to them. So there is a noise vector that gets added that gives us an image G. So we have G equal to HF plus N. This is one of the ways to denote imaging. Now there are some key aspects here. One is that there is F, so there is variability in population. So there is variability in F itself. So we need to build account for the statistics of that. There is the imaging hardware H itself, which causes some kind of transformation on the object F. Then there is also statistical things that need to be accounted for due to the noise of the imaging system. So therefore, each of these components need to be considered very carefully when performing an objective assessment of image quality study. Again, ideally, this should be conducted with scanners, but again, there are a lot of logistical challenges in being able to conduct these studies with scanners. One of which is that either we have patients being scanned on scanners, or we have some kind of phantoms which are very human-like, also called anthropomorphic phantoms, but there's not such a large number of phantoms available. In contrast, now I already showed you simulation-based phantoms that are available. So you could use the simulation-based phantoms, and we could use multiple tools that are available to realistically describe the imaging process. This includes Monte Carlo-based tools, analytical tools. There is things such as GATE, which are very, very realistic. Then there are things such as less realistic, but are much less time consuming. One of them being ASIM, for example. An excellent resource for this is this website, nmmitools.org, where we can find a lot of these image simulation-based tools. So then we come to the third part, which is the process to extract task-specific information. So this requires an observer, a strategy to extract the information. An observer could be something that uses the projection data that we've obtained using our imaging system, uses an observer, gets some kind of test statistic, and if the test statistic is greater than some threshold, then decides that the signal is present, otherwise decides that the signal is absent. An observer could also be a strategy for an estimation task. So now here we have some projection data, G. We do a reconstruction of the image. We get a reconstructed image F hat. Our goal is to estimate the tracer uptake within a small region of interest here. So we have an estimator theta hat that operates on this reconstructed image F hat. Sorry, an estimator T that operates on F hat to give us the estimate, which I call theta hat. Now, it's not reconstruction will not necessarily be required, and there are approaches that have been developed that directly quantify from projection data. So these approaches directly work on the projection data G to give an estimate theta hat. Not going to the details here, but I'm happy to discuss about these different kinds of strategies later. So to extract task-specific information, one approach could be to use human observers, such as radiologists. Well, this would be the best strategy actually if we can find them, and they could devote the time to do this. But this is kind of logistically challenging. What are some of the challenges that this audience here can think of as far as using human observers for extracting task-specific performance on detection tasks? So let me give you an example, right? I mean, I'm at WashU. I have okay. There are some answers that are already coming up.
It's expensive.
Expensive, yeah, that's a good point. It's expensive. There's variability between observers. Very good point, Cassidy. In fact, I had not even mentioned this point in my notes, and I'll put it now. Time consuming. Oftentimes, these image quality studies are performed with lazy. That's a good point, but I'll not put it in my slides. So here's another way a euphemism to frame this would be to say it's tedious. So yes, it's tedious. It's time consuming as well. Uh, so even at an institute where we have radiologists, to be able to get their time, they are busy reading the clinical scans, and they have to do this image quality analysis and evaluation over thousands of images. It's definitely not a very ideal scenario. So what we would like, so here's, so what we would like is some kind of mathematical observers, which we could implement computationally, and then we would identify this method looks promising. Let me approach my radiologist, Dr. X, so that they can now evaluate this algorithm on the eventual detection task. So
Right.
such mathematical observers would be very nice.
If I may just comment, for example, you get a new scanner or even a new kind of scanner, and you're trying to, and we talked about the MLEM and the OSCM algorithms before in this class. So you could do one iteration. Let's say we fix the number of subsets to 16 or 20 or whatever. So do I want to do one iteration, two iterations, three iterations, four iterations? So now you get a lot of options. And you can also play with the number of subsets. You could play with the post smoothing. So there's so many combinations, and you cannot have, a clinician look at all of them with many different examples. So obviously it becomes more and more time consuming. And what Abhinav's saying is that you could try to maybe narrow it down using your computer observers, and then perhaps present to them. Do I understand correctly, Abhinav?
That's a great example, Arman. Thanks for presenting that. Yeah, so with that beautiful example, I think that even more emphatically makes the point on why we need some kind of mathematical observers, which we could implement in our labs and don't have to ask the radiologist to look at all these thousands of images and then they hate us after a while. So and there is a lot of literature on developing such observers. One of the observers is called the ideal observer. This observer is ideal because it is ideal. And I'll tell you what that means. So it uses the ratio of the probabilities of the measured data given the hypothesis. So this is using a concept referred to as the likelihood. I won't go into details here, but the key point is that it captures all relevant task-specific information from the image. No observer can do better than this observer on the detection task. Then this is as quantified using figures of merit that I'll mention later, such as AUC and true positive fraction and false positive fraction. So this observer is therefore called the ideal observer. There's nothing better out there. And any observer claiming to be better than this observer, well, I would take that with maybe a bottle of salt. So there is no observer that's actually better. The problem with this observer is that it's very difficult to compute. It requires knowledge of probability distributions under both hypotheses, which means that, okay, if there was a tumor that was present, what's the probability of the image data in the entire patient population where the tumor is present, and what's the probability of the image data in the patient population where the tumor is not present. So this is often unavailable. Even if it were available in a simulation-based setting, it's computationally very intensive to compute. So an alternative to that is linear observers. One of the linear observers was proposed by Harold Hotelling. It's referred as a Hotelling observer. It provides the best discrimination performance of all the linear observers, and so it's referred to as the optimal linear observer.
So, Abhinav, if I may comment, so the way I tend to think of the ideal observer is, as you said, it's an observer that knows everything, except whether in this particular image you're seeing the tumor is present or absent. But it knows everything. It knows if it's present, what are the distributions. It knows if it's absent, what are the distributions. The only thing it doesn't know is whether in this particular image is presented with, whether the thing is present or absent. Would that be a
yeah, thank you for clarifying that, Arman. Yeah, so it knows all the probabilities. Thank you for clarifying that, Arman. So what it knows is the probabilities, but it does not know, when given a new image, whether the tumor is present or absent. It uses these knowledge of these probability distributions to make an inference. Think of the ideal observer as some very advanced algorithm that knows that, okay, in these patient populations where the tumor is present, I knew that this is how the image should look like. And in these patient populations where the tumor is not present, this is how I know the image looks like. I will use this knowledge that I have so that the next time I get a particular patient, I'll make an inference on whether this particular patient image has a tumor or not. So the ideal observer does not know whether the tumor is present or not. It just knows the distributions. And thanks for clarifying that again, Arman. The next task is one of estimation. So for this purpose, there are multiple estimators that are present, one of which is maximum likelihood estimator, one of my favorites. Then we have the maximum a posteriori estimator, posterior mean estimator, and these are becoming more important in the context of using prior information as can be obtained from deep learning. In fact, we have shown in a recent study that the posterior mean estimator is obtained when you use, for example, a CNN for the task of estimating a certain parameter. In this case, it was the parameter of tissue fraction effects. Of course, building upon previous literature in statistical estimation decision theory. So when you use a CNN and that minimizes the mean square error, or it minimizes the binary cross entropy loss function, and it's estimating some parameter, that the estimate that it's getting is the posterior mean estimator. So again, this builds on all the literature on statistical estimation theory, but with the CNN being used as a tool to implement that particular cost function. Then there's this Wiener estimator, and then more recently a scanning linear estimator has been proposed, which has also shown incredible performance. That gets me to the final component of the OIC study, which is the figure of merit to quantify task performance. Now, consider that we have a detection task, right? So we have two hypotheses. I see that there is a question. Let me just... So Arash has a question on what about the cost of each method, time and expense. I think it should be, yeah, I agree with you, Arash. And actually, again, I'm not going into a lot of details on this, but the way these observers are derived, they actually account for the costs. So there's a cost of making an error. There's a cost in of saying that if the tumor is present and you say the tumor is absent, or if the tumor is absent, then saying the tumor is present. So there are costs that are associated with that. Now, what you're referring to is time and expense, and those would be additional cost parameters that could be incorporated. The ideal observer actually, that's a very good point again, because it allows me to tell you that the ideal observer actually accounts for these costs of making errors and tries to find out the decision strategy that kind of minimizes these costs. But I did not specifically talk about time and expense as the cost here. And I believe that these can also be incorporated into the decision strategy. Okay. So now here we have a figure of merit on detection for detection tasks. So like I was saying, let's assume let's consider two hypotheses, signal present and signal absent. So that's the truth here, right? So we have an image that comes in. Either the signal is present, signal could be tumor, and the signal could be absent. So that's H0, the tumor is not present. Now you make a decision, right? We decide that the signal is present. If the signal is actually present, we have done a good job, great job, right? That gives us what we call the true positive fraction, right? Truly positive. And now the signal could actually be absent, and we decide the signal is present. So this is not good. And this is saying falsely calling positive, because we're saying the signal is present, whereas in reality it was absent. So this is called as the false positive. And when you divide it by the total number of cases, we get a fraction. So I'm using the term false positive fraction here. Now, another decision could be deciding if the signal is absent. Now, if the signal is present, not good. And we have falsely called negative. So it's the false negative fraction. Now, the signal could be absent, and we decide the signal is absent. Great job, true negative fraction. As it turns out, the true positive fraction plus the false negative fraction is 1, and so are FPF plus TNF equal to 1. Now, oftentimes, I showed you briefly this in the previous slides, we have like a threshold, and the observer decides based on a threshold that is the signal present or absent. So as we vary this threshold, we can get a plot of the true positive versus false positive fraction, which leads to a receiver operating characteristics, or an ROC plot. Not gone into any details of how you form that plot here. I just want to probably show this plot. So here on the x-axis, we have the false positive fraction. On the y-axis, we have the true positive fraction. And here is my ROC plot. And if I had more time, I would have gone through how we actually draw this plot. It's a very nice exercise to do. It often gets the students really engaged. but I would probably skip it here. What I would want to show here is that the area under this ROC plot called the AUC is often a single scalar figure of merit to compare observer performance on detection tasks. An excellent reference for this is Charlie Met's paper in Radiological Phase Technology, 2008. Now, moving on, figure of merit for estimation tasks. Here, the goal is to quantify the performance on the task of quantifying some numerical or statistical parameters of interest, right? So what are some of the metrics that you can think of? If the goal was to quantify how accurately I measured something, what would be a figure of merit? Bias, maybe? But then if the goal was to measure something precisely, what would be the figure of merit then? Would bias be a good figure of merit, or would I look at standard deviation or variance? And then if the goal was to say, well, I care about both bias and variance, I want to look at overall reliability, then a figure of merit such as mean square error would be very helpful. So these are some of the figures of merit that I used: bias, variance, and ensemble mean square error. Now, very briefly, I'll talk about figure of merit for joint detection estimation task. This is done using this EROC analysis. A great reference is paper by Clarkson in JOSA A 2007. So in summary, OIC-based evaluation, objective assessment of image quality, can be performed, and there are methods that are available for this. It requires following 4 components, where it has 4 components, and it requires us to follow those 4 components rigorously, and then we can actually objectively evaluate the systems. A second part of this lecture, which I think I have much time for, I want to talk about some practical examples of conducting objective image quality.